anyway. So what is a small add map? Well, let me remind you that operators which act on vector spaces form a linear vector space of their own, as I have been saying, and operators which act on this vector space, the vector space of operators, is what we are calling superoperators. And the add map, small because it's written with small a, what it does is that it maps operators to superoperators. So this is actually one step above superoperators. Superoperators have a domain of the set of operators and a range of the set of operators. It maps operators to operators. We map operators to operators. The add map has a domain of the set of operators. The range is the set of superoperators. But anyway, what exactly is the superoperator which add maps to? So what it does is it associates each operator or maps each operator a hat with a superoperator add a hat. And you have to define the superoperator, of course, by its action on an operator. So what does add a hat do to B? It's defined to be the commutator of A with B. So the commutator of an operator with another has now become a superoperator add a hat acting on the operator B. Now it's easy to see that for each a hat, add a hat is a linear operation. It's a linear superoperator. That is, if you replace B here by C1 B1 plus C2 B2, by definition as a commutator of A with C1 B1 plus C2 B2, and a very basic property of the commutator is that this becomes C1 A commutator B1 plus C2 A commutator B2, and this piece of course is add A acting on B1 and this piece is add A acting on B2. So add A is linear because if you replace its argument B by a linear combination, you get a linear combination of results. So for each A, add A is linear. Well, the add map which maps A to add A is also linear in the sense that if you were to talk about what add maps C1 A1 plus C2 A2 to, it is C1 add A1 plus C2 add A2. This is something you should check for yourself, and the way to check it is very easy. You just apply this map on an arbitrary B and see what happens. Show that the effect of the left hand side, that is which is C1 A1 plus C2 A2 commutator with B, an arbitrary B, is the same as the effect of the right hand side. That's a very trivial property of the commutator again. So what we have seen is for every map A there is a superoperator add A which is a linear superoperator, and this mapping between A to add A is also a linear mapping. Now what is really important for us, what makes add operators so important, is the result which follows from the commutator of add A and add B. This should not come as a big surprise. After all, we are dealing with rotations and angular momenta, and commutators play a very big role there. So it should be sort of obvious that the reason why we brought in this detour about small adds and so on has something to do with the commutator. So let's see what the commutator of add A and add B is. Of course, a way to figure out what the commutator is to make it act on an argument which is an operator C and see what happens. So let's start with add A times add B acting on C, and as always add A times add B acting on C is defined by add A acting after add B acts on C. So it's add A acting on B commutator with C. This of course is add B acting on C, and that's the repeated commutator, A's commutator with B's commutator with C. What about add B add A C? Very similar, and that's B commutator A commutator C. So what is the commutator of add A and add B acting on C? There's a difference between these two results, of course, and we will massage it into a slightly more familiar form by switching the sign, switching the order of A and C here at the expense of changing this minus sign to a plus. Why do I say this should be more familiar? because anybody who has studied commutators would know that one very important property of commutators is something called a Jacobi identity. The Jacobi identity is simply this: if you take the commutator of A with B and C, with the commutator of B and C, and carried out a cyclic permutation of the terms, the sum is 0. This is very trivial to prove. If you have not done it before, you should definitely do it now. You just write them out in full and you will see all terms cancel. But the reason why this is important for us right now is what we have here for add A, add B commutator acting on C is just the first two terms of the Jacobi identity. So what that means is this is nothing but negative of the last term left, and I can change it into a positive sign just by switching the two things in the first commutator, that is A comma B comes first and C goes after that. But now this is nothing but adjoint of A comma B acting on C, and since this works for arbitrary operator C, what we can say is add A is commutated with add B is nothing but what the map add maps the commutator to. So the map add maps operators to superoperators, but this is a map which respects commutation in the sense that if you take the commutator of two operators and map it, the result is the same as a commutator of the two individual mapped superoperators. So the superoperator add A add B commutator is add AB commutator. This is a central, very important result for add, which is why small add is so important for us. Technically we say this is a Lie algebra homomorphism. If you don't know about Lie algebras right now, don't worry, this is just terminology right for the time being. We are not going to use any Lie algebraic properties in the rest of the lecture. But later on, when you go on to study Lie algebras, as most of you will realize why this is important. For general Lie algebras, why this is important for us? Basically because the commutator between adjoint J1 and adjoint J2 will be adjoint of IH cross J3, which is IH cross times adjoint J3. That's the kind of relation that's going to be very important for us. But before we move on to go to seeing how this small add map works in the context of angular momentum, let me just introduce to you briefly the big add operator. There is also a map, why big add? Because it's spelt with a capital A. The big add operator is also, like the small add operator, a map which carries operators to superoperators. So it carries, in particular, it carries operator A hat. So add A hat with capital A to a new superoperator, which is the exponential of the superoperator add A. So the map adds with big A maps an operator A to a new superoperator. Which superoperator? Well, the exponential of add A, by the definition of exponential, is just identity plus add A whole square by 2 factorial and so on. Just to remind you, the square, the cube, etc. of an operator simply means the operator acts several times. So what does this big add A do? On an arbitrary operator B, what we have is add A acting on B is nothing but this whole thing acting on B. But that I can write in a compact fashion as this sum acting on B, right? 1 by n factorial, and the sum goes from 0 to infinity, with 0 factorial of course being 1, and add A acting n times on B. But what is add A acting on n times on B? Well, add A acting once on B is the commutator of A with B. Add A acting twice on B is A's commutator with A commutator B. Add A acting on 3 times on B will be A's commutator acting on A's commutator, acting on A's commutator with B, and so on, repeated commutators or n-fold repeated commutators. You must remember that we met this in a rather big way when we talked about the Becker-Hausdorff lemma. And in fact, the Becker-Hausdorff lemma is actually what we are aiming at here. According to the Becker-Hausdorff lemma, add A acting on B is simply e to the A, B, e to the minus A. Why is this useful? Well, we saw that the way in which an operator changes under an infinitesimal rotation of coordinates is basically the operator gets acted upon by the superoperator, by the identity superoperator that gives you O back, minus I epsilon by H cross times add n hat dot j, which is why you get a commutator of n hat dot j with A. This is the infinitesimal version. What happens for finite rotations? We've already seen that before. Essentially, the infinitesimal part becomes exponentiated, and so you basically have u1 theta inverse O u1 theta, where u1 theta inverse essentially is e to the A. I will leave you to work out the details yourself. This is pretty straightforward, but you should realize that if you know what happens with small rotations, you can figure out what happens with big rotations. As we have said, that happens both at the level of action on states, where operators get exponentiated. Here is the superoperator which is acting on the operators. We are talking about what happens to operators. So it's a superoperator acting on operators, and the superoperators are generated by the components of angular momentum. However, we are taking commutator there, so basically you have a small add operator acting, and its exponential, the big add operator, is what gives what acts on the operators for finite rotations. Now let us leave this big add operator for the time being. Let's go back to the small add and recast our findings about the spherical vector operator in the language of small add, and try to understand why you had this huge similarity between the action of j plus j minus j0 on the small j equal to 1, m equal to plus 1 minus 1 0 eigenstates, and the commutator of j plus j minus j0 with the vector operators on the other hand. Well, as we had seen, and we had stressed this rather a lot, that the adjoint operators obey the same commutation relations as the corresponding operators do. That is what the Lie algebra homomorphism is all about. So for angular momentum in particular, add ji commutated with add jj is ih cross epsilon ijk add jk. Of course, the sum is always there, although we very often drop this sigma sign in favor of the Einstein summation convention. This of course is what follows from the fact that ji commutated with jj is ih cross epsilon ijk jk. So this is exactly the same algebra as the original angular momentum operators. So just like the angular momentum operators have eigenstates, in particular J3 has eigenstates, Jm eigenstates with mh cross as eigenvalues, and J plus minus do certain things to them, you expect add J3 to have eigenstates, and the eigenstate structure should be identical to what the J3 eigenstate structure is. After all, if you recall the angular momentum theory that you studied in the last semester, you worked out the eigenstates of J3 just by using commutation relations, right? So since add J1, add J2, add J3 have the same commutation relations as J1, J2, J3, we expect the same kind of eigenvalue structure here as well. But there's only one important thing. What exactly does it mean when we say eigenvalues and eigenvectors for superoperators? Add J1, add J2, after all, are superoperators. Well, remember, the superoperators act on a linear vector space whose elements are operators. So the eigenoperators of add J3, for example, must be operators. But operators on which action of add J3 returns the same operator with a multiple. And we already have seen them. Remember, this was what the commutation relations of Jz with v plus 1, v0, v minus 1 look like. But in the language of the small add operator, this is nothing but small add Jz or small at J3 acting on V plus 1, V0, V minus 1. Notice a superoperator acting on the operator gives you that operator back with a multiple. This is exactly an eigenvalue equation. Just to rub this in, let me side by side show you the action of the Jz operator on the states. So when Jz acts on the states 1, 1, 1, 0, 1 minus 1, then exactly the same factors. Again, the typo that was there before is continuing. This is minus h cross, so this minus h cross here is alright. And you don't really stop there. What happens with the other commutation relations? These are j plus v plus 1, j plus v0, j plus v minus 1 acting on each other. Of course, these are not eigenvalue equations. You don't get v plus 1 back, you don't get v0 back, you get other things. But these are really the action of the add j plus operator on v plus 1, v0, v minus 1. And the parallel of this with j plus acting on the states 1, 1, 1, 0, 1 minus 1 is complete. There is a factor h cross which I forgot to put in here on this side. Similarly, j minus, again modulo this h cross which is missing. Sometimes, of course, in theoretical physics we pretend that whenever we have forgotten the h cross, we pretend that h cross is 1, but this really is a typo. But forget the typo, look at the structure, exactly the same behavior, and that is not surprising because this behavior, this entire behavior was dictated by the commutation relations which Jz, J plus and J minus had with each other. And at Jz, at J plus, at J minus may be superoperators, they may act on operators, but they have exactly the same commutation relations. So their eigen vectors which are operators of at Jz will behave the same way, not a surprise at all. So this is a reason why spherical vector operators essentially behave exactly like angular momentum eigenstates. But now you must be wondering, why stop at spin 1? For any j, you have j3 jm is mh bar, j plus minus jm is like this. Now these were consequences, remember once again, of the commutation relations. And since add j plus, add j3, add j minus have the same commutation relations, you can of course think of 2j plus 1 dimensional eigenrepresentations of the add operators, which means that for each whole number j, we have a set of 2j plus 1 operators tjm, where m goes from minus j to plus j, which have exactly the same kind of behavior, except for the fact that when instead of j3 acting on jm, you have j3's commutator with tjm, but that is really add j3 acting on tjm, and j plus minus commutator with tjm giving you this. The notation is slightly different. Instead of writing them in a ket, of course these are not kets, these are operators, and we typically write the j upstairs to just show that the m index is the index which changes within a particular set. So these 2j plus 1 operators form what is called a spherical tensor operator of rank j. Well, just like spin 1 and spin 1 added to give you spin 0, spin 1, spin 2, if you take the product of two spin 1 operators, which is two vector operators, you of course formed the tensor operator of rank 2. That was a Cartesian tensor operator of rank 2, a 9-dimensional subspace. This is a direct product subspace of the two 3-dimensional spaces. And just like in the theory of addition of angular momenta, this 9-dimensional direct product space broke up into 3 irreducible subspaces, one corresponding to j equal to 0, 1-dimensional, another corresponding to j equal to 1, 3-dimensional, and a 5-dimensional one corresponding to j equals 2. Here you see exactly the same. So the answer which we started this lecture with, y is 3 times 3 equals 1 plus 3 plus 5 even for vector operators as it is for addition of angular momenta, the answer is it's the same mathematics reflected at one step higher Earlier you had operators acting on states, direct products decomposing in a particular manner. Now you have superoperators, which are commutators with other operators, acting on operators, direct products of operators decomposing in exactly a similar manner. Now this behavior is really very important. These operators form an invariant set under rotation of coordinates. Of course, what happens to the operators under rotation of infinitional rotation of coordinates is basically they change by add j3 times or add j plus, add j minus, or some combination acting on tjm, and they form a new combination of tjms. And for finite rotations, you just build them up out of small rotations. So they form a linear combination of tjms. This is why they are so important. When you rotate, they just mix among each other. And they form an irreducible set. There are no smaller subspaces which mix among each other under all rotations. Now these commutation relations play a very, very important role in deriving many important results for rotation in quantum mechanics. And one very important result that we get is the Wigner-Eckert theorem, which tells you how to relatively easily calculate matrix elements for spherical tensor operators, objects which obey these commutation relations. In the next lecture, we are going to look at some specific examples of spherical tensor operators, higher rank ones. We have already seen rank 1. We are also going to see how to use a Wigner-Eckert theorem, and we are also going to see how to combine spherical tensor operators, and the answer should be sort of intuitively obvious. You will see the Klebsch-Gordon decomposition back all over again. All this is for the next couple of lectures. I will just leave you with one query. Notice that here I said whole number j. Remember, if we were starting just from the commutation relations of j3 with j plus minus, we could have whole numbers as well as half integers or half odd integers. Here we only have whole numbers 0, 1, 2, 3. I will let you worry about why that is the case. Why is it that just like orbital angular momentum has only whole number values for L and the odd half integers don't show up, why is it that the odd half integers don't show up here? For spherical tensor operators, you just have whole numbers. The question is why? Well, we will discuss this also in a later lecture, but you should think about it yourself.